The next lesson that we will be talking about is about partial fractions. Our main objectives are the following. First one is we are going to use systems of equations to decompose proper and improper rational expressions into sums of simpler expressions. The second one is to decompose partial fractions with different kinds of denominator like distinct linear, repeated linear, distinct or irreducible quadratic and repeated factors. So in this kind of rational expression, we have here 2 over x squared minus 1 equals 1 over x minus 1 plus negative 1 over x plus 1. So these are just equal, but the expression on the right side, which is here, is these are called the partial fraction decomposition of 2 over x squared minus 1. So again, this one is the partial fraction decomposition of this one. So it is possible to write any rational expression as a sum of rational expressions whose denominator involve power of polynomials of degree not greater than 2. If function of x and g of x are polynomials and the degree of f of x is less than the degree of the g of x, it can be proved that in this equation f of x over g of x equals f sub 1 plus f sub 2 plus dot 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 and f sub r. So as stated here that degree of f of x is less than the degree of g of x. So therefore, the partial fraction decomposition is only applicable if the f of x or the degree of the f of x is less than the degree of the g of x. So such that each f sub k has one of the forms, so a over px plus q squared or ax plus b over ax squared plus bx plus c raised to n. So where the a and b here, they are real numbers, wherein m and n are the non-negative integers. And the quadratic polynomials ax squared plus bx plus c is irreducible over r. That is has no real zero, so the sum f sub 1 plus f sub 2 and so on plus f sub r is the partial fraction decomposition of f of x over g of x, and each f sub k is a partial fraction. So here are the guidelines. So the guidelines for finding partial fractions. So the first guideline is if the degree of the numerator f of x is not lower than the degree of the denominator g of x, use long division to obtain the proper form. So if later we have an example that will fit in this guideline, that if the degree of the denominator, I mean the degree of the numerator is not lower than the degree of the denominator, so what we need to do is we try to use the long division so that we can be able to find or to fit the or to meet the requirement that in order for us to conduct the solution for the partial fraction decomposition is that the degree for the numerator must be lower than the denominator. So the second one guideline is the factor factor the denominator g of x into a product of linear factors px plus q or irreducible quadratic factors ax squared plus bx plus c, and then collect repeated factors so that g of x is a product of different factors of the form px plus q raised to m or ax squared plus bx plus c raised to n for a negative integer m or n. So the third guideline is we are going to apply the following rules to the factors found in the guideline 2. So the first rule is for each factor of the form px plus q raised to m when m is equal but greater than 1, the partial fraction decomposition contains a sum of m partial fractions of form. So we have here a sub 1 over px plus q plus a sub 2 over px plus q squared plus and so on a sub m over px plus q raised to n. So where each numerator a sub k is a real number, so it is constant. So the second rule, for each factor of the form ax squared plus bx plus c raised to n, wherein the n is with n is equal but greater than 1, and ax squared plus bx plus c irreducible, the partial fraction decomposition contains a sum of n partial fractions of the form. We have here a sub 1x plus b sub 1 over ax squared plus bx plus c plus a sub 2x plus b sub 2 over so and so on. So a sub n x plus bn over ax squared plus bx plus c raised to n. So where each a sub k and each b sub k is a real number. So the denominator, so we have also the as stated in our objective, is the different kind of denominators of partial fractions. So here it is. So here they are. The first one is the distinct linear factor. So the distinct linear factor is goes like this. So a over ax plus b. So which means if we have a factor x minus 1 times x plus 2. So if we have a factored form like this, so we could say that their roots is distinct, or therefore we could say that it is under the distinct linear factor. So they have distinct linear factors. So wherein a is a constant, of course. So the second one is repeated linear factors. So the repeated linear factors, if we're going to find the partial decomposition for this kind of or for some rational expressions, is what we need to do is to put into like this. So a sub 1 over ax plus b plus a sub 2 over ax plus b squared, and so on until how many or what higher degree the given has, or the factor of the given has have. So we know that if as based on the description here, is that if it is repeated linear factor, so assuming if we have a factored form x minus 1 times x minus 1, so we could say that this is a minus 1 squared. So this kind of example will fall in this one. So this one. So where a sub 1, a sub 2, and then a sub k are constant, and a sub k is not equal to 0, and then k corresponds to number of partial fractions. So the third one is the distinct or irreducible quadratic factor. So based on the description here, is that the quadratic factors or quadratic from the based on the algebra, is it I think it came from the quadratic functions. So you are going to transform, so for a given or irrational expressions, in order to be partially decomposed, we need to transform this one into like this. So it's it is equal to ax plus b over ax squared plus bx plus c. So take note that this is a quadratic equation, wherein there the rational expression is not factorable, so there is no factor or roots here. So where a and b again it is constant. So the last one is the repeated. If the distinct linear factor has repeated a linear factor, so the same also with the quadratic factors. So the last one is the repeated quadratic factor. So the same concept with the repeated linear factors, but the only main difference or the comparison between the two is that the instead of just a constant in the numerator, here is we have now ax plus b. So ax plus a sub 1x plus b1 over ax squared plus bx plus c plus a sub 1x plus b1 over ax squared plus bx plus c squared, and so on until such time that we until you meet the highest degree, or in the a sub k x plus b sub k over ax squared plus bx plus c raised to k, wherein a1, b1, a2, b2, ak, bk here are constant, and the ak and bk not both zero, and then k corresponds to the number of partial fractions. So in order to understand the concept that we had discussed earlier, is that we try some applications for it through example problems. So our first example is we are going to apply, or um, it is a partial fraction decomposition in which each denominator is a linear. So our goal is to find the partial fraction decomposition of our given rational expressions 4x squared plus 13x minus 9 over x cubed plus 2x squared minus 3x. So first step is we need to inspect that is this rational expression do fit in our first guideline, that the degree of the numerator must be less than the degree of the denominator. And by inspection, yes, it is less than, because the degree of the numerator is 2, while the degree of the denominator is 3. So we can now apply the partial fraction decomposition. So again, this example is under the linear, uh, distinct linear factors. So what we need to do is, so applying the concept that we have discussed earlier, is that uh, uh, we need to factor, or to find the factored form of our denominator. So in so our first step is here. So we know that x raised to 3, or x cubed plus 2x squared minus 3x. So we need to find its factored form. So first one is we need to move out, or to uh, to to uh, to put outside the x, and then the remaining terms would be x squared plus 2x and then minus 3. So our next step here is to find again the factor for the x squared plus 2x minus 3. And we know that the factored form for it is that it is equal. So this one is equal to x plus 3 times x minus 1. So just copy the x. So now, based on the roots that, the factored form that we had, or the roots, so we could say that they are it falls under the distinct linear factors. So they are distinct with each other. So the roots for this one is x is equals to 0. The second root is x minus x equals to -3, and then the third root is x equals to 1. So let's proceed to the partial fraction decomposition. So based on the rules, or the concept that we had known earlier, is that we need to transform them into like this. So we put the so first one is let's say a over x for the first factor, a over x plus b over x plus 3 plus c over x minus 1. So there is a question sometimes, most of the students before said that, sir, what if I putted b over x, a over x plus 3, a plus x. So assuming if we have a over x plus 3, and then plus b over x plus c over x minus 1. So what if, sir, if we have, if I inputted my equation like this, so instead of this, so I have a different kind of equation, a over x plus 3 plus b over x plus c over x minus 1. But what I could say that that's okay, even though you have just different in terms of a b c that you inputted, but still in the last in the final answer you will arrive in the same answer. So that's okay, even though your a is not basta as long as your x plus 3 and then x minus 1 you are I mean you have the correct or the precise factored form or the factor for the given rational expression. So no matter what the A, B, C, or the subscript that you use here, so that's okay. In the last or in the final answer, for sure you will be arriving in the same answer. So if you have the rational expressions like this or the partial fraction decomposition like this and also here, so you just try it and for sure you will arrive in the same answer. So next, let's proceed. So after that, we know again that the factored form for our denominator is this. So what we need to do is to let's multiply all sides in here. So let's multiply all side and then let's multiply also in the let's multiply this one, the factor from here to the left side, and then we also multiply this one to each term in the right side. So we know that x times x plus 3 x minus 1 is equal to x squared plus 2x squared minus 3x, right? So if you are going to multiply this one, this will be cancelled out. So the remaining would be 4x plus 13x minus 19. So next is in the right side. So first term first, the first term, so a over x. So if we multiply this one in here, so the x will be cancelled, but we have the remaining expressions is x plus, or the factor form is x plus 3 times x minus 1. So here it is, x. So we are done with this. So a so next in the second term is if we multiply x plus 3, so the remaining is, so the x plus 3 will be cancelled. So the remaining would be x and then times x minus 1. So here it is. So the last one, if we multiply this uh, in the last term of the right side, is the remaining would be x and then x plus 3. So here it is. And then what we need to do is just let's simplify. So find the let's simplify this equation, or find the let's apply distributive property. So a x squared plus 2x minus 3 plus b, so x times x is x squared, x minus 1 is x, plus c, x squared plus 3x. So next step is we need you need to uh, to find the simplest form for this. So use the distributed property. So that's one of the techniques. So and then after that is we need to segregate all the coefficients, or I mean let's segregate the coefficients in according to the degree of the variable. So if the variable is x squared, so let's group them, let's group them by the variable, or what degree of the variable in the problem or in here. So if we have so the first one is let's group the coefficients for the x squared. So in here we have only a, we have the a, and then uh, we have b in here, and then in the c is we have also c. So this is c. So for our x, in terms of x, we have 2a, 2 times a, so this is 2a. So bx, we have x also here, so this is negative b. Also in the last one is we have 3x, so 3c times x, or it depends on the solutions you have. So if you are going to distribute them one by one, so that's okay. So in this kind of method, so I use the shortcut, or the short method. So for the constant, for in terms of constant only, so in this one, so yes, we have a constant, negative 3a. So in the second one, we have no constant here, constant term, and also in the last one, we have no constant term. So after that is we need to do is what we need to do is so here it is. So we need to equate the coefficients. So this is one of the methods that is really applicable also in the preceding, I mean in the next subject that you will be encountering, or like differential calculus, integral calculus, or even in differential equation and advanced mathematics. So this partial fraction is really, it is relevant in the subjects. So in this method is we need to equate the coefficients for this one. So this is equating the coefficients so of this one. So first one is we need to equate the coefficients for x squared. So for x squared, so this is also okay. For x squared, uh, so here is we have for x squared in their left side we have 4. So we have 4. So this is it. Okay. So the equals is like the barriers for these two. So okay. So in the left side we already, yes, we have 4. So again we are just equating the coefficients. So the coefficients only. So you are only inputting or just state here only the coefficients of the functions. So in the right side x squared is, so yes, so all the coefficients for x squared, so this is 1. So a plus b plus c, so here it is. So wala nang iba. So next one is what we need to do is let us going to equate the coefficients for x. So this is the equated equation. So again the equal sign is the barrier for them. So in the left side x we have 13. So just write 13 here. And then in the right side, so here it is 2a minus b plus c. So here is the equated coefficients. Then the last one is for constant. So let's assume that constant or x raised to 0, assuming that this is our subscript for the constant. So let's equate the coefficients for the constant. So in the in the left side we have only negative 9. So this is negative 9. And then in the left side we have only negative 3 a. So let's negative 3a. So at this point we could say that our a here will be equal to, so this is negative 9 divided by, so if negative 3, so negative divided by negative 3, because so our a is equals to positive 3. So we could say that again our a is equal to positive 3, and then all you need to do is just substitute the positive 3 or the value of a in here, and then also in here, and then use the elimination or substitution in order to solve for the b and c. And then uh, after that, if you arrive at the correct solution or the correct answer, our b is equal, so in this kind of problem our a, yes, it is equal to positive 3. So using this equation we can easily solve the a, and then our b is, so after numerous solutions that you have, is our b is equal to negative 1, and then our c, it is equal to positive 2. So after that is you need to substitute the the ABC or the so this one into the uh, partial fraction decomposition that you had last time. So hence, so the partial fraction decomposition is 4x squared plus 13x minus 9 over x cubed plus 2x squared minus 3x. So again our a is positive 3. So 3 over x. So And then b is negative equal to negative 1, so this is negative 1. So negative 1 over x plus 3. And then the last one is our c is positive 2. C is positive, so positive 2 over x minus 1. So this is it. So therefore, this is our final answer. So therefore, the partial fraction decomposition of 4x squared plus 13x minus 9 over x cubed plus 2x squared minus 3x is 3 over x plus minus a negative 1 over x plus 3 plus 2 over x plus 1. So this is our answer.